In this section, we're going to talk about heat as a form of energy and how when heat is applied to materials, it can cause temperature to change as well, and the factors that are going to influence that temperature change. So here we have, in our scenario, a Bunsen burner generating heat energy. It's been converting the chemical energy of the natural gas to heat. And as the Bunsen burner operates, heat is going to be transferred to the beaker. And then the beaker is going to warm up, conduction will occur, the water will begin to heat up. And as the water heats up, heat is transferred to the block of aluminum. So the way we define heat is the idea that it's the internal energy that can be transferred from an object of high temperature to low temperature. So the Bunsen burner initially was the highest temperature. The glass becomes hot. The hot glass transfers heat to the water, and the hot water transfers heat to the aluminum. So we're going to take a look here at calculating energy changes when temperature actually itself also changes. So in the process of doing this, we can think about the factors that are going to influence the amount of heat that can be contained in an object. A large object, more massive object, can contain more heat. So the factors that determine the amount of heat that can be stored by an object or transferred from an object the amount of heat that is transferred are going to be mass. Now when an object transfers heat, as I mentioned earlier, the heat is going to go from the warm object to a cool object. In the process, the hot object will lose some heat and therefore experience temperature change. So there will be a change in temperature. This will be another factor, how much temperature change occurs. And then there's a property of the material that's called the specific heat. And this depends on the nature of the material itself. So we should take a moment and define this term, specific heat. So specific heat can be thought of like thermal inertia. And when we say thermal inertia, what we're saying is the resistance to change in temperature. So an object with high specific heat will resist temperature change. What does that mean? Well, it is the amount of energy and so we're going to get our change here, the amount of energy needed to change 1 gram of substance by 1 degree Celsius. So let's say here, we can look at the idea that a large specific heat requires a lot of energy, which means it has a high resistance to change. And this term here actually can be also symbolized. We use the symbol capital C. And in our case, we're going to be doing everything at constant pressure with the lower subscript P. So we're going to look at an activity here where we're going to actually try to study how to determine the heat capacity of material or look at a process where heat is transferred from one object to another. So let's take a look at this diagram. Here we have our hot water and our aluminum. Let's say that we got the water up to 100 degrees Celsius. We let it sit long enough that as a result the aluminum is at the same temperature as the water. We say that's at thermal equilibrium. So the temperature of the water, heat was transferred to the aluminum, hot object to cold object until they reach the same temperature. We want to study the property of this aluminum block. Let's say that also when we looked at our properties, we said that we need to know the mass of the block. So let's say this block here has a mass of 50 grams. Now over here on this side we have some cold water, and let's say the cold water here is 40 grams. So we have a mass of cold water sitting here. Now what we're going to do in this experiment is we're going to transfer the heat from the hot block to the cold water, and by doing that study the actual material itself. So we're going to pick up this block, carry it over here. I'm going to place the aluminum block, now the hot block, in the cold water. Well, what's going to happen? The heat is going to flow from the hot block to cold water until they reach thermal equilibrium. So this was originally 100 degrees. This was originally 20 degrees Celsius. At some point in time, the temperature is going to become equal. If we let this sit, when this reaches thermal equilibrium, we make a measurement. We put a thermometer in here. Here's our thermometer. We watch the thermometer. We observe the temperature. And let's say that the temperature of the thermometer at this point in time, at thermal equilibrium, is 30 degrees Celsius. So what's happened? The block absorbed heat from the hot water. It's now stored that as internal energy. We move that block to the cold water. It now begins to lose heat to the cold water until they reach some temperature. The temperature we've set here, as we measured it, turns out to be 30 degrees Celsius. What we want to understand here is what's going on in terms of the ability or the thermal inertia of this block. So how can we think about the process? Well, there's two things that are going on. What's occurring is that the block is losing heat and the water is gaining heat. So we can think in terms of logic. We can say that the heat lost by the block is going to be equal to the heat gained by the water. And since we can measure this process and we know something about water, then we can actually continue to evaluate what takes place. So the heat lost by the block depends on the mass of the block, the change in temperature of the block, and the heat capacity, CP, of the block. That should be equal, conservation energy, to the mass of the water, the change in temp of the water, and the heat capacity of the water. What do we know about the block? We know the block is 50 grams. We know that the block went from 100 degrees Celsius, because that's how hot we got it, and it cooled down. Let's take a look real quickly to where it cooled down at thermal equilibrium to 30 degrees. So to 30 degrees C. And here we have a quantity we don't know. This is our heat capacity. So in this case, we have a piece of metal. We don't know the heat capacity. We can interpret that. On this side, we had some water. Okay, let's review again. We had 40 grams of water. And originally, the temperature of the water was cool. It was at 20 degrees C, and it went to 30. So we have our 30 degrees C. minus 20 degrees C. Now, people have studied water quite a bit, and they've learned that the heat capacity of water is 4.18 joules per gram times degrees Celsius. All right, so this allows us to do some mathematics and solve for the heat capacity of this material.